Hello students, let us continue with chapter 6 Problems and Solutions part 2. Question 6.1. Predict the direction of induced current in the situations described by the following figures. So A. The direction of induced current is usually determined by using Lenz's law. Let us see what is Lenz's law. The polarity of induced EMF is such that it tends to produce a current which opposes the change in magnetic flux that produces it. So this is Lenz's law. And you can see the diagrammatic representation of Lenz's law when north pole is directed towards the coil. We see there is an increase in magnetic flux and there will be a repulsive force. A north pole will be induced in the coil and current will be in the anti-clockwise direction. And if north pole is directed away from the coil, as you can see here, if it is directed away from the coil, then it produces a decrease in magnetic flux and therefore attractive force occurs at the coil and therefore a south pole is induced in the coil which will give rise to a clockwise current. So these are the factors which we are going to use to determine the direction of induced current in the following situations. So let us take the first case of the coil here. So here we have south pole directed towards the coil. So what happens? There will be an increase in magnetic flux which will cause repulsion at that end. So to cause repulsion, the right end of the coil should be south pole. And therefore clockwise current has to be induced at the right end according to Lenz's law. And therefore externally the current flows along QRPQ. Now look at the second case here. We have two coils. The left side, the first coil, you can see the south pole directed towards the coil at the right end. So what happens to the first coil? Increasing magnetic flux induces south pole at the right end of the first coil. And therefore clockwise current gets induced at the right end. So current flow will be along PRQP through the first coil. But what about the second coil? You can see the north pole is directed away from the left end of the second coil. When it is directed away, there is a decreasing magnetic flux at the left end, which makes that end of the coil an attractive force. So a south pole will be induced at the left end of the second coil and therefore a clockwise current is induced there. Therefore, the external current will be along Y, Z, X, Y. Now this is the third case. In the third case, we have a coil with a circuit and another coil without a circuit. And there is a hint given that the tapping key is just closed. When the tapping key is just closed in the first coil, a current flows in anti-clockwise direction as shown in the diagram. When observed from the side of the second coil, the current flows in anti-clockwise direction. But when we observe from our side, it flows in clockwise direction. But when it is observed from the other side of the coil, it flows in the anti-clockwise direction. And it is an increasing magnetic flux. So this induces north polarity in the first coil. So repulsive force in the second coil induces north pole in the second coil. And therefore the induced current in the second coil will be anti-clockwise. The direction will be Y, Z, X, Y. Now in this diagram here, we have a plain coil on the left side of the circuit coil. So here the circuit is very clear to us. The coil in the circuit is in the anti-clockwise, has an induced current in the anti-clockwise direction. Rheostat change in the circuit decreases magnetic flux. You can see the arrow mark in the rheostat is towards the lesser side. So there is a decrease in magnetic flux in the circuit coil. And current flow is anti-clockwise in the circuit coil. It has north polarity. Now the decreasing magnetic flux induces attractive force in the other coil. So it induces a south pole in the coil on the left side. And this induces a clockwise current in the left coil along the direction Z, Y, X, Z. Now in this direction, there is no magnet, only two coils. Tapping key is just released in the first coil. So that means the current is decreased, so magnetic flux decreases in the circuit coil. So right end of circuit coil has anti-clockwise current flow, hence north polarity. But due to decreasing magnetic flux, it induces south polarity in second coil as it has attractive force. So the left end of second coil is therefore induced with a clockwise current because it has south polarity. And therefore the induced current direction is along X, R, Y, X. Here we have a current I decreasing at a steady rate, and the coil is placed in a perpendicular plane. You know, for a straight wire, the magnetic field will be along concentric circles in a perpendicular plane. So the field lines here are not cut by the coil, and there will not be any change in magnetic flux. So no EMF will be induced in the coil. (615) Another question. An air-cooled solenoid with length 30 centimeter, area of cross-section 25 centimeter square, and number of turns 500 carries a current of 2.5 ampere. The current is suddenly switched off in a brief time of 10 to the power minus 3 seconds. How much is the average back EMF induced across the ends of the open switch in the circuit? Ignore the variation in magnetic field near the ends of the solenoid. What is back EMF? The self-induced EMF is called back EMF. Back EMF opposes any change in current in a circuit like switching on or switching off of current. So when a current is suddenly switched off or switched on, there will be an EMF induced in the opposite direction, that is called back EMF. So here we have to find out what is the average back EMF produced. And there is a formula for back EMF, E equal to d phi by dt, where d phi is the change in flux given by NAB. N stands for number of turns of the coil, A stands for area of cross section, and B stands for magnetic field strength. Magnetic field strength is given by the formula mu naught N I by L. Mu naught is permeability in free space, N is the number of turns, I is the current, and L is the length of the solenoid. So when you make the substitutions, we get E equal to 6.5 volt. So the average back EMF induced in the solenoid is 6.5 volts. Next question, 6.16. A. Obtain an expression for the mutual inductance between a long straight wire and a square loop of side A as shown in the figure. B. Now assume that the straight wire carries a current of 50 ampere and the loop is moved to the right with a constant velocity V equal to 10 meter per second. Calculate the induced EMF in the loop at the instant when x equal to 0.2 meters. Take A equal to 0.1 meter and assume that the loop has a large resistance. So the diagram is shown. You can see here there is a straight wire carrying a current I and there is a a square loop of side A and they are separated by a distance x. And the square loop is in motion with a velocity v. So we have to find two things. First, we have to find what is the mutual inductance between the long straight wire and the square loop. Secondly, we have to find out what is the induced EMF in the loop. What is mutual inductance? Mutual inductance is the EMF induced in the coil due to the change in flux in the first coil or in the first wire. It is represented by capital M. And what is EMF induced? EMF induced in the loop is due to its movement due to change in area. Now, to work out mutual inductance, we have to take a small element dy of the square loop. Now, the small element dy has a, let us say, has a length A and a breadth dy. So, its area dA will be A into dy. So, the magnetic flux associated with the element dy, d phi will be B into dA. Because here area is the variable. So d phi will be equal to B into dA. And dA is equal to A, small letter A into dy. B is the magnetic field at the distance y. And B is given by mu naught I by 2 pi y. So d phi, when you make the substitution, d phi you know is equal to B into dA. So it is mu naught I by 2 pi y into A dy. So what is phi? You have to integrate. When you integrate, you get phi equal to mu naught I A by 2 pi integral dy by y. Now the integral has got limits from x to a plus x. So the limits of the square loop are the minimum is x and the maximum is a plus x. So when you integrate dy by y, you get log y base e with limits x, lower limit x and upper limit a plus x. So you get phi equal to mu naught I a by 2 pi log base e a plus x by x, which can be written by as a by x plus 1 inside the bracket. But mutual inductance phi equal to m into I. So we equate these two equations for phi, which we found out previously also. So mi equal to mu naught Ia by 2 pi log base e a by x plus 1. Now I is common in both and the I cancels and therefore m equal to mu naught a by 2 pi log base e a by x plus 1. So we leave the expression for mutual inductance like that. That is the answer for mutual inductance between the straight wire and the square loop. Second part is what is the EMF induced in the loop, in the square loop, because the loop is moving. So here we have E equal to B dash AV. A is the side of the square loop and it stands for the length or the distance which it moves. So it is given by B dash is equal to mu naught I by 2 pi x into A. A is the side of the square and V is the velocity with which the square loop is moving. So when you make the substitutions, you get E equal to 5 into 10 to the power minus 5 volt. This is the EMF induced in the loop. Next question. A line charge lambda per unit length is lodged uniformly onto the rim of a wheel of mass m and radius r. The wheel has light, non-conducting spokes and is free to rotate without friction about its axis. A uniform magnetic field extends over a circular region within the rim. It is given by B equal to, that is vector B equal to minus B0 K vector, where R is less than or equal to A, where A is less than the radius R, equal to 0 otherwise. What is the angular velocity of the wheel after the field is suddenly switched off? So you can see in the diagram a wheel with radius R, and in a small region of radius A, you can see cross marks, that is a magnetic field. There is a magnetic field induced there. And a line charge, lambda, is the charge per unit length which is lodged uniformly onto the rim of the wheel. And the wheel has a mass m and radius r. We have to find, when the wheel rotates, what is the angular velocity of the wheel when the field is suddenly switched off. So let us start. If magnetic field changes with time, the rate of change of magnetic field, then there is an EMF induced in the wheel given by epsilon is equal to minus d phi by dt. Now work done on the test charge Q around the periphery is Q into epsilon. That is the work done. But there is already an electric force on the test charge, QE. So work done by this force around the periphery is given by QE into 2 pi a, where 2 pi a is the circumference of the periphery, 2 pi a. So we have found work in two equations, equation 1 and equation 2, and we equate both expressions. We get Q epsilon is equal to QE into 2 pi a. Q is common, therefore E equal to epsilon by 2 pi a. But epsilon is already minus d phi by dt, as you see above. So when you make that substitution, you get E equal to minus 1 by 2 pi a d phi by dt. Now this is calculation here, but phi is b into a, and that is b into pi a squared. That is the area of where the magnetic field exists. Therefore, E is equal to minus 1 by 2 pi a squared d by dt. Here it is change in magnetic field, therefore d phi will be dB by dt. And therefore E equal to, if you simplify, minus a by 2 dB by dt. Now total charge on the rim, Q equal to lambda 2 pi a. Lambda is the charge on 1 unit. Therefore, total charge on 2 pi a units will be lambda into 2 pi a. And the force on this charge, F equal to Q into E, is equal to minus lambda 2 pi a into a by 2 dB by dt. But by Newton's second law of motion, force is mass into acceleration. And acceleration is rate of change of velocity. So we get m into a equal to m into dv by dt. But for rotational motion, we know v equal to r omega, where r is the radius of the wheel and omega is the angular velocity. So F becomes equal to m into d by dt of r omega, and when you make the substitution, you get minus lambda 2 pi a by 2 dB by dt equal to m into d by dt of r omega. or you take r outside, it's a constant, it is equal to mr d omega by dt. Therefore, d omega equal to lambda pi by mr squared a squared dB. And when you integrate both sides, you get omega equal to lambda pi by mr a squared b. So in vector form, we have omega angular velocity, we have omega vector equal to minus b into pi lambda a squared by mr into k vector or k cap. You get that as your answer. I hope you have understood. Thank you, students. We'll continue in the next class.